All right, greetings, scholars. Beautiful mind here. We're continuing our exploration on Chapter 5 of Polynomial and Rational Functions. And here we're going to be working on Section 5.3, Graphs of Polynomial Functions. Okay. So a few learning objectives here. In this section, you will recognize characteristics of graphs of polynomial functions, use factoring to find zeros of polynomial functions, identify zeros and their multiplicities, determine end behavior, understand the relationship between degree and turning points, graph polynomial functions, and use the intermediate value theorem. All right. So example 1, recognizing polynomial functions. Which of the graphs in figure 2 represents a polynomial function? Okay, so one characteristic of polynomial functions is that they don't have sharp corners or edges. So that one can't be a polynomial. So this one is not a polynomial. Okay, and then this graph here has holes or gaps or breaks. All right, so polynomial functions don't have holes or gaps or breaks, so this can't be a polynomial. So I would say the two remaining are polynomials. I would just say, yeah, this should be a polynomial and this should be a polynomial. Okay. Let me see. So f and h are graphs of polynomial functions. They are smooth and continuous. The graphs of g and k are the graphs of functions that are not polynomials. The graph of g has a sharp corner. The graph of function k is not continuous. All right. So a main property of polynomial functions is that their graphs are smooth and continuous. No sharp corners or edges, and no holes or gaps or breaks. Okay. So if you have a sharp corner, a hole or a gap or a break, then it's not the graph of a polynomial function. Let me see. I know you can't read that. Oh, actually, that's a repeat of what we just experienced. I don't know. I think I forgot to delete that slide, but that's okay. Do all polynomial functions have as their domain all real numbers? I would say yes, right? That's one characteristic of, once you identify a function as a polynomial function, in general, the domain of a polynomial function is all reals. Yes, any real number is a valid input for a polynomial function. So given a polynomial function f, how to find the x-intercepts by factoring? So first we set the function equal to 0. If the polynomial function is not given in factored form, then we have to factor out any common binomial factors and then factor any factorable binomials or trinomials, right? So, and then set each factor equal to 0 and solve to find the x-intercepts. So given a polynomial function, how do we find the x-intercept? We set the function to 0. Then we want to write it in completely factored form. When we go to factor it, first we want to factor out any greatest common factor, so any GCF, common to all terms, and then try to factor the remaining either binomial or trinomial, or whatever's remaining, we try to factor it further, right? So find the x-intercepts, okay? So for this, we have to set the function equal to 0. And I think here, let's get a copy of the original. So we have f of x equals, we got this x to the 6 minus 3x to the 4 plus 2x squared. If we want the x-intercept, we set our y, or set the function equal to 0 and solve. So now it looks like we do have a GCF, a greatest common factor. It looks like we can factor out, and that was fast. Wait a minute. I'm gonna try low power mode. I mean, it does help, but man, I was just at like 18%. Anyway. Okay, so the greatest common factor, it looks like we could factor out x squared from all the terms. If we factor out x squared, looks like we're going to be left with what? X to the power of 4 minus 3x squared plus 2. I'm going to use my technique of u substitution. I'm going to say let u equal x squared. I'm really doing it for that trinomial. I'm not really concerned with that first one as of right now. But I guess just for the sake of being consistent, I'll make it a u. We're going to have a u there and a u there. This is going to be what? U squared minus 3u plus 2, right? Again, I'm not really concerned with that first one. I guess we can kind of proceed. But now it should be easier to factor at this point. Oh no, is that dying too? Okay. We got a u, and u. Because the second sign is a plus, I know my signs are the same. Because the first one is negative, I know the larger one is negative. So that means they're both going to be negative. Okay, and I think the numbers are 2 and 1. Okay. So then now that we have it in completely factored form, we get that what? U equals 0, or u equals 1, or u equals 2. Right? And then we need to back substitute. So then this means what? X squared equals 0, x squared equals 1, or x squared equals 2. So then when we go to take the square root, we get x equals 0, x equals plus or minus 1, x equals plus or minus the square root of 2. Okay. So then, just put these in ordered pairs. But these are the results that we got. Man, my battery was not charged. I might have to, it was showing a false number. It started at 20. It's dropping. I guess it's not charged. It wasn't showing the real charge. Because it's like, it dropped from like nearly 20% to 6% in like a matter of minutes. I was like, okay, that's not right. I'm going to see how far I can make it though, without it dying. And I think what we have is correct. And then again, we just need to write those as ordered pairs. So find the x-intercept. So this one seems like it's a lot of factoring so far. I know. Let's see. Where's that adapter? I could go grab that adapter. Okay, give me a moment. Let me see if I can find this adapter. All right, good. Organization works. Oh, sorry. Battery is so low. So low that you can't hear it. All right. Oh, good chugga. I know I probably should edit this, but I'm not going to. All right. I'm just going to try to give it some. That's why we work. Okay. So hopefully you can still hear me. I guess I'll just have to check in my post-production to make sure that the audio is going through. That's gonna be a long time if it's not going through, but it should work. So, okay. Well, at least we're charging now. Okay. Okay, that's fine. So find the x-intercepts. So we want to set this guy to 0 and solve, and we have a polynomial with 4 or more terms. So we're probably going to try factor by grouping. Okay, so here's a copy of the original. X cubed minus 5x squared minus x plus 5 equal to 0. Okay, let me see. Okay, so usually whenever we have 4 or more, now first we do try to factor out any GCF. I don't think we have any greatest common factor here other than 1. So when we have 4 or more terms, we try to factor by grouping. So what I'm going to do, I'm going to group the first 2 together and the second 2 together. Now, if I factor out the greatest common factor, the GCF from the first 2, it looks like we can factor out what, x squared, and we're going to be left with x minus 5. In the second 2, it looks like I want to factor out a -1, and the goal, we want that common binomial factor. They have that same blue part, right? Okay, so now we can factor out the common binomial factor. In other words, they both have that blue thing. So we could factor out x minus 5 from both terms. And we're going to be left with x squared minus 1. Okay. Then we have difference of squares there. So that's going to factor x minus 1, x plus 1. All right. I'll keep working over here. So then our x-intercepts are going to be -1, 0, 1, 0, and 5, 0. Okay. All right, well, I'm glad I found this adapter because we are charging and you should be able to hear me. So let's see. I think we're good. And here's a pictorial representation of what we just experienced. So find the y and x-intercepts. Okay, so again, usually I like to find the y-intercept first because oftentimes it's easier to do than the x-intercept. So our y-intercept, we're going to set x equal to 0. That's going to be 4 times 3, 12. So 0, 12 looks like our y-intercept. If we let x be 0, we're going to have a -2 squared times 3. 4 times 3 is 12, right? But then for the x-intercept, I guess I'll work here. We set y equal to 0. So we're setting the whole function equal to 0. Actually, I'm just going to work over here. So we're going to have this. Now we got lucky because it's already in factored form. We got this x minus 2 squared times 2x plus 3 equal to 0. So we set each factor to 0 and solve. So we get x equals 2. X equals a -3 by 2. All right. Okay. So our x-intercepts should be what? 2, 0, and a -3 halves, 0. Okay, so we got those correct. I guess that's another slide I forgot to remove. That's fine. So like when I was creating these, this was the original slide. I guess I just forgot to remove it, that I like spliced and like zoomed in so that we can actually see it. I think I just forgot to do it because I did want that graph and I think I just forgot to edit that slide. Yeah, I got to go back and fix some slides, but that's okay. Find the x-intercept. Okay, so we're going to set the function to 0 and solve. So this is factoring. So yeah, so, you know, this section, this section is like heavy factor in orientation, right? It's heavy, a lot of factoring. If somebody requests it, I have like a chapter from like intermediate algebra devoted specifically to all the factoring scenarios. You know, it'll basically walk you through. It's a whole chapter. I have 2 documents. One document is a summary of factoring, how to approach a factoring problem, and then maybe I'll just go ahead and put it in the handout section in Box. So similar to how you access our notes, all right? There's a folder in Box that should say handouts. It should already be there, and I'll just try to check and confirm. But one is a single page PDF that summarizes how to approach a factoring problem. First, you find the greatest common factor. Then you identify, are you working with 2 terms, 3 terms, or 4 or more terms? When you have 2 terms, that's either like difference of squares, difference of cubes, or sum of cubes. When you have 3 terms, that's the main one that we do, where you see me doing the AC method of factoring. And then whenever we have 4 or more terms, we do factor by grouping like we did in the previous example. And then aside from that summary, I have a whole chapter devoted to factoring. So it gives examples and kind of walks you through pretty much all the scenarios that we'll see in this course for factoring. So I'll just try to make sure that it's in our handout section. So the way you access the PDFs, you know, there's a Box link. I think that I made that link available kind of towards the beginning of the semester in the discussion section, in the announcements section or whatever, the dashboard. So you'll see something that says PDF Box link. That's where like the notes are, and you can find those handouts that I was talking about that can help you with factoring. Okay. Let's see. So find the x-intercepts. So we're going to set the function equal to 0 and solve. We have this h of x equals, we got x cubed plus 4x squared plus x minus 6 equal to 0. Okay. Can we regroup it? 2 and 3. Because I'm not seeing, let me see. Oh, using a graph. Okay. So, yeah, because this one I'm not seeing like if we can factor it, but we could look at the graph, right? One thing that we noticed if we were just going to look at the graph, the leading term, this is an odd degree polynomial. The highest power is a power of 3. So that, and the leading coefficient is positive. So we know the graph goes up to the right and down to the left, right? The leading coefficient of is positive tells us the graph goes up to the right. The degree of the polynomial being 3 is odd, which means the other side does the opposite. So if in the long-term behavior, if it goes up to the right and down to the left, it has to cross the x-axis at least once, right? And at most 3 times. We have at most 3 x-intercepts, right? So we could like graph this, like put this in our graphing calculator and then look at the graph. Because I think that's what they want us to do here. Because this one, I don't think we can factor it. And if you were going to graph this by hand, you can get an approximation like that by choosing several values of x, find the corresponding y's. And then you're looking for like when the y values go from positive to negative, right? So whenever the y values change sign, you know that there's a 0 somewhere in that region. I'm just going to use my prepared notes here. But again, I think what they should be doing is putting this in like a graphing utility. Now, if you don't have a graphing calculator, again, some sites for free graphing, like free virtual graphing. I know a popular one for students is called Desmos.com. And another one is called GeoGebra. So these are free online graphing utilities. You might have to do a little bit of like Googling and research to figure out how to use them. But once you figure out how to use them, they're really useful for this kind of stuff. And it's free. So you don't have to go out and buy a $100 calculator, things of that nature. Okay. So let me see, this is not, it has no common factors and does not appear to be factorable using techniques previously discussed. Fortunately, we can use technology to find the intercepts. Keep in mind that some values make graphing difficult by hand. In these cases, we could take advantage of graphing utilities. So look at the graph of this function. It appears that there are x-intercepts of -3, 2, and -2 and 1. There are some other techniques that are available for finding zeros, but we haven't talked about it yet. But yeah, I think this one, they just wanted us to use a graphing utility and just look at the graph because it wasn't factorable, right? So they didn't expect us to factor this one. Okay, my battery is at least charging, right? This is a long section, by the way. We're almost halfway through. Let me see. Okay, that's fine. I kind of want to mention a technique that we could have used here. So there is a technique called the rational zero test. It involves taking the ratio of, I think it's I think I'm getting this part backwards. I'm not really sure, to be honest. It's our P over Q, where it's like the ratio of our leading coefficient over our constant term. And we like do all the combinations of like their ratio. And what this test will do, it'll generate a list of the possible rational zeros of this function, and then from that list, it's pretty much a guessing check. But we could have used that here, and I don't know if we're going to talk about that here or not. So I'm just mentioning, like, if you want to research that, the rational zero test, you could use it. But I'm just trying to save it for in case we officially talk about it. Like, I don't know why I can't get my words out today. But yeah, I just want to save it for now. So for something like this, I would use a graphing utility for now. Okay. So graphical behavior of polynomials at x-intercepts. If a polynomial contains a factor of the form x minus h to the power of p, the behavior near the x-intercept h is determined by the power of p. We say that x equals h is a zero of multiplicity p. The graph of a polynomial function would touch the x-axis with even multiplicities, and the graph will cross the x-axis at zeros with odd multiplicities. The sum of the multiplicities is the degree of the polynomial function. So given a graph of a polynomial function of degree n, how to identify the zeros and their multiplicities? If the graph crosses the x-axis and appears almost linear at the x-intercept, it's a single zero. If the graph touches the x-axis and bounces off, it's a zero with an even multiplicity. If the graph crosses the x-axis at a zero, it is a multiplicity with an odd. It's a zero with an odd multiplicity, and the sum of the multiplicities is less than or equal to n. Yeah, let's kind of work an example to kind of dig a little deeper into that. Use the graph of this function of degree 6 in figure 9 to identify the zeros of the function and their possible multiplicities. Okay. So the zeros occur at our x-intercept. So we have like one here. There's one here. And then like one here, right? So the zeros would be x equals -3, x equals -1, and x equals 4. And the corresponding multiplicities, all right, the multiplicities, when x is -3, notice it touches and bounces, so that has an even multiplicity, right? So it's going to be raised to some even power, that factor. When x is -1, it crosses. I think that has a multiplicity of 1. Now, when x is 4, it still crosses, but it's not linear, so that has an odd multiplicity. All right. So it's going to be, it should be raised to some like power, like maybe a cube or some odd power other than 1. Okay. Yeah, I just forgot. I messed up a lot of slides there. I meant to remove this slide as well. Okay. Oh, I forgot about the degree. Oh no, we already told that it's degree 6. Okay. So the sum of the multiplicities must be 6. Starting from the left, the first zero occurs when x is -3 and the graph touches. So it must be an even multiplicity. So it most likely has a multiplicity of 2. Okay, that's fine. The next zero occurs when x is -1. The graph looks almost linear, so it has a single zero of multiplicity of 1. The last zero occurs when x is 4 and it crosses, so the multiplicity must be odd. And then we know that the multiplicity is likely 3 and that the sum of the multiplicities is 6. So that's fine. All right, so we could have taken it a step further and said that the first multiplicity was 2. All right, some even, and they said it's most likely 2. And then the second one, I think we got that one because it crossed the x-axis and it was almost linear. So that one had a single zero of multiplicity 1. And then since they have to total 3 and the last one is some odd other than 1, the last one had a multiplicity of 3. Okay. Let me turn this on. Noise. Oh yeah, I gotta update that. I just realized. Okay, I'll do that a little bit later. Okay, I think we're officially halfway. So determining n behavior. So I think we mentioned this in the previous section. Like this is leading to this thing called the leading term test. So to kind of recap, with a positive leading coefficient, our graph goes up to the right, up to the right. With a negative leading coefficient, the graph goes down to the right, down to the right. So the leading coefficient tells us about the right-hand side of the graph. If the degree of our polynomial is even, then the other side does the exact same. The other side does the exact same. If the degree of our polynomial is odd, the other side does the opposite. It does the opposite. Okay? So the leading coefficient tells us about the right-hand long-term behavior of the graph, and the degree of the polynomial tells us about the other side, whether it's the exact same or the opposite. Okay? That's fine. I'm just going to let that be for now. So a turning point is a point on the graph where the graph changes from increasing to decreasing or decreasing to increasing. A polynomial function of degree n will have at most n minus 1 turning points. Find the maximum number of turning points on each polynomial. Okay, so the degree of the polynomial in part A is degree 5 because that's the highest power. So then it has at most 4 turning points. If we were to expand B out, it would be what, a power of 4? So that means we have at most 3 turning points. Okay, I think we got those correct. So given a polynomial function, how to sketch the graph? Okay. Before I read this, when I'm sketching polynomials, just in my leisure time, just for fun, right? Because that's what I'm doing in my free time, sketching polynomial graphs. If I were going to sketch a polynomial function, a polynomial by hand, first I'd like to investigate my intercepts, and I usually start with my y-intercept and then my x-intercept. We could do a test for symmetry. I don't know if we've talked about symmetry here or not, but we can do a test to find out whether it's even, odd, or neither. And so that helps out a lot. We can explore like turning points. We might have at most a certain number of turning points. Now, if we were in calculus, we have ways of exactly finding those turning points, but that's a calculus discussion. We talked about intercepts, symmetry, a few additional points. What else have we talked about? Let me see. So a few additional points and then put those together for our purposes. So let's see how the book suggests. We can find our intercepts, do a check for symmetry. Okay, so that was the even, odd, or neither. Use the multiplicities of the zeros to determine the behavior. So we could talk about the end behavior of the graph, like what happens in the long term. The multiplicities tells us about how the graph behaves around the intercepts, so we can use that information. So we can use our leading term test and then put all this together. Ensure the number of turning points does not exceed 1 less than the degree of the polynomial, and then optionally use technology to check the graph. Okay. All right. So here we're asked to sketch the graph. So I'm going to need some space. Let me see. Okay. So for our purposes, again, a good place to start are the intercepts. Okay. And then I like to start with the y-intercept. To find the y-intercept, we set x equal to 0. Okay, so let's start here. So if we set x to 0, that's going to be a 9 times negative 2 is negative 18. So it's like 18 times 5. 20 times 5 is what, 100? But then that's 10 too many, so it should be 90. So the y-intercept we get is 90. Okay. So then if we can find the y-intercept, that means we can find the x-intercept. And we set y equal to 0. Now I think we got fortunate here because it's already in factored form. So then we get -3 and 5. All right, we set each factor to 0 and solve. We can also talk about the multiplicity. So when x is -3, it has an even multiplicity. So it should bounce off the x-axis. This one is going to bounce. And when x is 5, it has an odd multiplicity. So that one's going to, and it's linear, so it's going to cross nearly in a straight line. So it's going to cross the x-axis. Okay. So that's using the multiplicity. Okay. Let's do a test for symmetry. Okay. So to test for symmetry, what we're gonna do is replace each x with -x and simplify. Right. Let me do a quick recap. So a function being even, the definition of a function being even means what? When we have f of -x, we get back to the original. The definition of a function being odd, when we evaluate f of -x, we get a negative times the original. Okay. So then what we're going to do again is replace each x with -x, simplify, and then see if we can generate one of these two cases. So first I'm going to replace each x with a blank set of parentheses. And in the blank parentheses, we're going to put -x. Okay. Now in that first expression, if we factor out -1, if we factor out a -1, we're going to have what? -2 times x minus 3 squared. I don't think we can. Let's keep going. We can factor out a negative here as well. We're going to have what? X plus 5. You know, I don't think that we can get, this isn't the original, and I don't think that we can get to a negative times the original. So I would say there's no symmetry. Or what type of symmetry do we have? There's none. Let me kind of work over here. So I guess we can like explore the local behavior, like using the leading term test. We'll just say, and then we could talk about like turning points. So I'll just say like local behavior. Okay. So like from the leading term test, if we were to expand out the original, it would be what? A degree 3 polynomial? Okay. So the degree of the polynomial is 3. So then our leading term, because you have to expand it out to find this, our leading term is going to be negative 2x cubed. Okay, negative 2x cubed. So that means our leading coefficient is negative 2. Okay, so because our leading coefficient is negative 2, that tells us our graph goes down to the right. And because the degree of our polynomial is 3, which is odd, that means the other side does the opposite, so it should go up to the left. We have at most 3. Now I think, yeah, well, we have all 3. We have at most 3 x-intercepts. And at most 2 turning points. Okay. Let's go here. Number 4. I'm just going to say a few additional points. Okay. So usually I'll do my few additional points I do between and beyond my x-intercepts and vertical asymptotes. We're not doing vertical asymptotes here just yet. So a few points between and beyond your x-intercepts, So, we have when x is -3 and 5. So maybe like when x is -5, -4, maybe -2, -1, 1, 2, 3, and 6, right? Just a few points between and beyond your x-intercepts. So now, and again, I'll just say, I'm just choosing some x values, and we use a table. So like, we could say like x versus f of x, right? And then like some x values I would choose might be something like -5, -4. We can do like, let's do -1, and then 2, and like let's do 6, right? Again, I just chose a few x values between and beyond my x-intercepts. So I would choose these x values, find the corresponding y, plot the points, and then just basically put all this together. So we plot our intercepts. I don't think we had any symmetry, so we couldn't use that. We know that the graph should go down to the right and up to the left. We actually do have 3 x-intercepts because the -3 has a multiplicity of 2, so that counts as 2 of our x-intercepts. So even though we only have 2 points listed, the -3 counts for 2 to make all 3. All right, and then again, we can use a graphing utility to find the corresponding y's. We're just going to plot a few points and put it together. I think I'm actually going to use the prepared notes instead of sketching it by hand. But we can confirm that all of this stuff shows up in the graph. Okay. And again, we just chose several values of x and found the corresponding y, and plot a few additional points. Okay. All right, let's see. Has 2 x-intercepts. We got the y-intercept, that's fine. We know it goes down to the right and up to the left. We said that, okay. I think we got all that. Okay. So then with the multiplicity, I think we said that -3 had an even multiplicity, so it should bounce off the graph. And it's not going to cross the x-axis before we get to it, so it should bounce above the x-axis, all right? And then we also had it crossed the x-axis when x was 5, right? Notice that this graph is bouncing when x is -3. It's crossing when x is 5. We have our y-intercept of 90 is going down to the right, up to the left. And then, we chose several values of x. So like when x was -5, I know we had -2. I think we had maybe 2, and I know we had 6, right? So we just chose a few additional points. You put it all together, it looks like this. Okay, that was interesting. Yeah, I think we got all of that. And there's no symmetry, right? So we couldn't use that. Okay. So with the intermediate value theorem, let f be a polynomial function. The intermediate value theorem states that if f of a and f of b have opposite signs, then there exists at least one value c between a and b where f of c equals 0. Now, we actually mentioned this earlier. When I know in one example, we were trying to find the x-intercepts and we could not factor it. So then we diverted to like using a graphing utility. And then I was suggesting one way to find x-intercepts manually. So suppose you didn't have the graphing utility. If you choose several values of x and you kind of keep going, and then you kind of want to pay attention to where you have a sign change, right? Say when x was -3, y was positive, and when x was 2, y was negative. So there has to be a 0 somewhere between -2 and -3, right? So that's actually the intermediate value theorem, right? So when your y values go from positive to negative or vice versa, there has to be some x between those corresponding x values that where the graph crosses the x-axis. Because again, we're working with the polynomial functions, and the main characteristics of polynomial graphs are that the graphs are smooth, continuous, unbroken curves. So because the graphs are smooth, continuous, unbroken curves, it's not going to change sign without crossing the x-axis, right? Or the y values aren't going to change signs without crossing the x-axis. Okay. So show that this function has at least two zeros between -1 and 4. Something like this, I would use my graphing utility in the form of a table, right? So what we can do is create a table and look at the x values from -1 to 4. So I'm like, maybe here, let me pull up my graphing utility. Let's see, I think if I go, let me go here for now. I know it's a little bit off the screen. Let's go here, and I'll go ahead and pull this over here so you guys can see it. Come on, thank you. Reload and refresh. Okay. So this original x cubed minus 5x, oh no. Nope, that's not what I want. Let me see. I don't think I can make that bigger. I think one thing. Let me go to my y equals. I guess I could just write it. That would help me. So we have this f of x equals x cubed minus 5x squared plus 3x plus 6. Or I can just type it. Let's just do that. Yeah. I'm just trying to get a copy. Give me a moment because I got to type this in. So we have what? X to the power of 3 minus 5x squared plus 3x plus 6. Okay. There we go. Come on. Okay. All right. I think that's good. So now what I want to go, I'm going to hit second table set. I want the table to start at 1 and change by 1, and I'm going to look at the table, right? So when we look at these tables of values between 1 and 3, notice that our y values start off positive, it goes 0, then it goes negative, right? So somewhere at least you can say somewhere between 1 and 3, because it goes from positive to negative. Oh, well, actually, that's one of our zeros, right? Yeah, so I'm up here trying to find the 0. One of the zeros is 2, so we got lucky there. And then, but notice that the sign goes from negative to positive between 3 and 4, right? When x is 3, y is negative. When x is 4, y is positive. So that means that there has to be a 0 between 3 and 4, right? So just with those 4 alone, we get 1 0 because when x is 2, so that's one of our zeros. And then the second 0, we can use the intermediate value theorem because the y value goes from negative to positive. So there has to be a 0 somewhere between when x is 3 and 4, right? Just by looking at the table. So let me make a copy of this table available. What I'll do is kind of like that and like that is good. I'm just going to include it in notes. And I'm going to zoom in, paste, crop. So this is basically a reiteration of the same image. One of them just showing the whole calculator, another one I'm kind of like zooming in a little bit. so you can see it better. Okay, so show that this function has at least two zeros between 1 and 4. So one of the zeros is 2, so that's one of them. And then when x is 3, we get a negative number, and when x is 4, we get a positive. So there has to be a 0 somewhere between 3 and 4 because we have a sign change and we're working with a polynomial. Okay, so that counts for our second 0. So we see that 1 0 occurs when x is 2. Also, since f of 3 is negative and f of 4 is positive, by the intermediate value theorem, there must be at least one real 0 between 3 and 4. So we have shown that there are at least two real zeros between 1 and 4. Okay, so that was fun. Okay. And you can see the zeros here. Or you can see here's the graph of this. Okay, so writing formulas for polynomial functions. If a polynomial of lowest degree p has horizontal intercepts at x equals given, then the polynomial can be written in factored form, okay? Where the power is pi on each factor can be determined by the behavior of the graph at the corresponding intercept, and the stretch factor a can be determined by giving a value of the function other than the x-intercept. Given a graph of a polynomial function, how to write a formula for the function. Identify the x-intercepts of the graph, examine the behavior of the graph at the x-intercepts to determine the multiplicity, find a polynomial of least degree containing all the factors found in the previous step, use any other point on the graph. The y-intercept must be the easiest to determine the stretch factor. Okay, let's give this a go. This sounds interesting. Write a formula for this polynomial function shown. Okay, so we can quickly identify our x-intercepts. Let me see. That one's almost linear, I guess. So we have what? -3, 2, and 5. And notice that the 2, the graph bounces off the x-axis. So that should have an even multiplicity. We have what? 1, 2, 3 turning points. So that means we should be working with a degree 4 or higher polynomial. Also, and it should be even because the end graph behaviors go in the exact same direction, right? So to put all that together, if -3 is a 0, that means that x plus 3 is going to be one of our factors. If 2 is a 0, that means x minus 2 is a factor. Now let me add this on there. This is going to be what? F of x equals some a times all of this. Okay. Because 5 is a 0, that means x minus 5 is a factor. And again, because the graph bounces when x is 2, this one more than likely has a degree 2, right? And then it said that you need some point other than the x-intercepts. So if we do the y-intercept when x is 0, the y-intercept is -2. So then that means we would have what? A times 3 times, what is that, a 4? Times -5. So when x is 0, the corresponding y is -2. 12 times 5 is -60. Ooh. I'm not liking that. I mean, that could be the case though. So our a potentially could be, we divide both sides by -60, we get what, 1/30? So then this function potentially could be 1/30 times x plus 3, x minus 2, oh, wait a minute. Yeah. X minus 2 squared times x minus 5. Okay. Let's try this in our graphing calculator and see if we can compare. So I'm going to go to my y equals, and I'm going to put parentheses 1/30. And then we got an x plus 3 times x minus 2 times, oh, that's x minus 2 squared times x minus 5. Okay. And I guess we can just do a standard window. Yeah, that looks pretty good. It's fairly close to what they have. -4 is like the lowest, yeah. And we could change the window to match theirs, but I think we're good enough. Okay. So this is what we got. That was interesting. Yeah. Yeah, I think they did exactly what we did. All right, less than 10 slides ago. We're almost there. So local and global extrema. A local max or a local min at x equals a, sometimes called a relative max or min, respectively, is the output at the highest or lowest point on the graph in an open interval around x equals a. If a function has a local maximum at x equals a, then f of a is going to be greater than all nearby f of x for all x in the open interval around x equals a. If a function has a local minimum, then f of a is going to be less than or equal to all f of x for all x in the open interval. A global max or global min is the output of the highest or lowest point of a function. If a function has a global max at a, then f of a is greater than all f of x for all x. Similar for minimum. We can see the difference between local and global extrema in figure 21. So we have a global max, a local max, and a local min, right? So we're basically with max and mins, we're talking about the peaks of the mountains and the bottom of the valleys, right? So there's no global minimum because it goes down forever, right? So every time you choose a number, you can always find a number lower. But with something like this, we do have a global max. We call this a local max just because it's a peak, but it's not the highest peak. And this is a local minimum because it's the bottom of a valley, but it's not the smallest number. It's not the smallest y value, right? Do all polynomial functions have a global min or a global max? I would say no, because if it's an odd degree polynomial, that means it's going to go in opposite directions forever, right? So there's not going to be a global max and a global min. You might have some local max and local mins. Sorry. But when you're working with an odd degree polynomial, you won't have a global max or min. Those are going to only occur when you're working with an even degree polynomial, right? Like something like x squared, you're going to have a global minimum, or max depending on your leading coefficient. No, only polynomial functions of even degree have a global min or a global max. For instance, f of x equals x has neither a global max nor a global min. An open box is to be constructed by cutting out squares from each corner of a 14 centimeter by 20 centimeter sheet of plastic and then fold it up on the sides. Find the size of squares that should be cut out to maximize the volume of the enclosed box. Enclosed by the box. Okay. So this one is fun. So it sounds like we're starting with a rectangle. All right. Piece of plastic. We're going to let our plastic be blue. Something like this. Let's go style. We're going to fill, actually. Let's go style, stroke, like this, fill, like this. Can we make that more translucent? That would be nice. I'm pretty sure I can. But I'm not seeing that option. That's okay. Okay. And we're going to cut out squares. Okay. Okay. Now, so an open box is to be constructed is 14 by 20, right? Centimeters. So this is 14 centimeters. This is 20 centimeters. Then we're going to fold the flaps up to make an open box. Sorry, I just made it a little bit style. Okay, I think this is good. All right. So basically the dashed lines are behind like a wall or a surface or whatever. So you get like a 3D effect. Okay, that was fun. So an open box, I mean, this is fine. Now I'm doing some other stuff in my mind, but this is fine. An open box is to be constructed by cutting out squares from the corners. Is 14 by 20, okay? And then folding up the sides. Now, we don't know the size of these x's, so that's what we're trying to solve for. So, like, from here to here is x, okay? In order to maximize the volume, okay? So, let's get an expression for the volume in terms of x. So, now, if we cut out a square that's x by x, the x is going to show up in our final product over here. What is this? X centimeters here. That's going to be from here to here, right? So that's what we're going to have control over. So then, if that's x, we're going to have this remaining. All right. If we're cutting away x, and that means that this is going to be what? 14 minus 2x. So this is going to be 14 minus 2x from like here to here. And so in this graph, that shows up here. Let me see. So this is going to be 14 minus 2x from there to there. Okay. And then we're going to have this 20 minus 2x that's going to run from here to here. Okay. So then the volume of our box is going to be length times width times height. So it's going to be x times 14 minus 2x times 20 minus 2x. Okay. So then we want to find them. We want to maximize this guy. So we need to find the peak, right? We can expand this. And then look at the graph, right? Let's go ahead and do that real quick. I'm just going to kind of look at the graph. 14 minus 2x and 20 minus 2x. Probably should zoom outside of the standard. Let me think. Yeah, we gotta change our window. Hope my dog stays quiet. Got the alarm going off. We need to zoom out. So now we might have something. Let's see when x is, let's look at the table. For instance, when x is like 5 or 4, let's look at the table. Okay, so when we look at the corresponding y values, let's see, it looks like we got like a 336. So a proper window we might need to go up to like almost 400. Yeah, let's change our window. So the y value, the max, we need to get up to like 400. Let's go in steps of 25. Yeah. Or we could go in steps of 40. Let's see. 16 steps. Let's go in steps of 40. Okay. So then I'm going to go to calculate. Hang on, did I stop it? Okay. I want to go to calculate and I want to find the maximum value. So I'm going to hit number 4. And a left bound, I just want to get to the left of this value. I'm going to hit enter. I'm going to go to the right of this value. Hit enter, and then I want to get close. Just trying to get a sense. Come on. Okay, so it looks like when x is about 2.7. Let me see. What else can we do? What are we missing? Yeah, I mean, according to that, and this is an approximation, this is saying when x is about 2.7 centimeters. That'll maximize the box. Because if we expand it, yeah, I just used a graphing utility. I just kind of looked at the graph for that. Let's see what the book is doing here. So notice that after the squares are cut out, we get something like this, and I think we got this 20 minus 2x, right? I think we got all of that. Okay, yeah. So then notice that since the factors are these 3 zeros respectively, because the height of 0 is not reasonable, we consider only the zeros of 10 and 7. Okay, that's fine. The shortest side is 14. Okay, so they're restricting, it says we restrict the domain between 0 and 7. That's fine. Using technology to sketch the graph on the reasonable domain, we get an image like this. And we can estimate the value for the volume to be reasonable from 0 to 7. Okay, that's fine. So from the graph, we turn our focus on the domain from 0 to 7. We can estimate the maximum value around 340 cubits, right? Which occurs when it's about 2.75 centimeters on each side, right? So I think we got 2.7 using hours, and they got something close. So here, to find that peak, it was kind of like guess and check. We just looked at the graph and found what x value gave us that peak value. In calculus, we have a way to exactly find it. That's why I was kind of pausing, because I kept wanting to use techniques that I know are in calculus. I was like, dang, we hadn't talked about any of that stuff. So the only thing that we really had access to for something like this was actually just looking at the graph and using the graphing utility. Okay. If I say graph one more time, my head is going to explode. All right. Because, man, I said it like 12 times in like 3 seconds. Okay. Anyway. But yeah, we ended up using the utility. So. All right, and so with that, we're going to go ahead and end this session here. And from one beautiful mind to another, enjoy the rest of your day. Take care. Peace.